everyone. My name is Malvika Gupta, and today we are going to discuss the partition algorithms required for performing quicksort. Okay, so because in quicksort, as we know that we need to have a pivot element, and with the help of that pivot element, we will be dividing our array into two parts, and then we will be we'll sort that given set of array. All right. So we have three of this type of partition algorithm. One is knife, which we are going to discuss in this particular video. Then we have a Lomuto partition, and then again, and the other third one is the horse partition. So before starting ahead, we'll be discussing the knife partition, which is the basic rule which we use when we perform the concept of quicksort. Before moving ahead, let us discuss what we are going to use in this particular video. So I'm going to discuss about the introduction of this knife partition and little bit of quicksort, then pseudocode, how we can perform the knife partition, and an example with the help of which I'm going to explain you that how you can perform it, right? So the first part is the introduction, as I have already told you that quicksort, because as I said that yes, we have to partition it. Partition means that based on any element, if you are going to perform a partition algorithm, it means you are going to perform division. It means divide. Then again, I am telling you that we are going to sort. Once after dividing, we'll have to perform the sorting algorithm. It means it is a part of, this quicksort is a part of divide and conquer algorithm. Okay, so this is a part of divide and conquer. In this video, I'm not going to discuss that how we are going to perform quicksort once we have got the pivot element. But in this video, we'll only be sticking to that how to get that pivot element or not. Okay, how to get that particular pivot element. Pivot element is an element with the help of which we will be able to partition our algorithm, our arrays into two parts, and then we'll provide it to the quicksort function, and then the entire sorting process will follow. So for this, we have three types of partition algorithms, generally a knife algorithm, then there is a Lomuto partition algorithm, and there is one more which is called horse partition, right? The advantage of quicksort is this. You can also see this, that this is an in-place sorting technique. We generally used to say that, but it is not a stable sort. It is in place, but it is not a stable sort. This is the problem with quicksort. This is the basic problem, that because if there is a pivot element present, then how could you say that, right? In the case of Lomuto and horse, it is not stable. But in case of knife is the only partition method where you can say that it is a stable method. The elements occurring in a particular order will always come in the same order in the resultant array. Okay. Knife says that if suppose I am having an array of like this. Suppose I'm just taking an example, 5, 13, 6, 9, 11, 12, 11, and 8, suppose. Okay. So this is my array of 7 elements. Okay. So if in the knife, always remember your pivot element will be the last element. Pivot equals to the last elements, because now I'm focusing on the knife. I will be focusing on these two in the upcoming videos. But first of all, let's discuss this knife. So in the knife, your pivot element will be your last element. Always remember this. Okay. And this 8 you have to place in such a way in the array that all the values less than 8 will come on one side, whether it is sorted or unsorted, that doesn't matter, but it will come on the one side, and all the greater values to 8 will go to the right hand side. Okay, so it will be like 5, 6, and your 9 will go to the left side, and greater values will be your 13, 12, and 11. This will go to the right hand side. Okay, and this is not a matter of concern for us. For partition, it is only required to place the pivot element at a particular position, and then we can perform that combine or the sorting process. Okay, so that we'll do in once we'll complete with this one. Okay, now remember that in this case, you are not going to consider this pivot as a part of your sorting or your division. When you are calling the recursive function, this pivot will not be. Your array will run from 0 to pivot minus 1, and from pivot plus 1 till your last index. Always remember this. Okay, fine. So we will be starting with the knife method, that how I am going to perform this knife method, right? So once first of all, we are going to write the algorithm, the pseudocode for this one, or sort of a kind of a program I'm going to write, and then I'll be taking an example to tell you that how it is going to perform. Okay. So now let's write it. Suppose this is, I'm giving the name to the, suppose partition. And in this partition, there's an array. Okay. Lower index, I have writing higher index because there's nothing like right, left and right. If you want, you can write it. And there will be a pivot element because pivot index is also decided. So if you go for with this case, so I'm writing this array also over here. So that will be easy for me. 2, 5, 13, 6, 9, 12, 11, and last one is the 8 one, right? So suppose, so 0, 1, 2, 3, 4, 5, and 6. So my L is 0. My high is n minus 1, which is 6. And my pivot is at 6. Okay. And element is 8. Okay. Now let's begin with this one. So first of all, let's do it. So first of all, let me create a separate array so that I can put my elements into that. We'll see how to do it because we have to perform some partition and then we'll keeping it to that. Okay. So let me create an array. Suppose I am creating an array of temporary, name temporary, right? And the size of this array will be L minus H plus 1. The size will be N, basically. Okay. And for this, I am taking one to run this one. I'm taking an index, which is there we have in, as we can take, you can take any variable like K, I, whatever, because I and J generally we are going to use in the entire array. So I'm taking it as index so that it will help me to run this part. Now I'm running a for loop, and this loop will run from my lower index till my higher index. Complete. Okay. Including the pivot element also. And I plus plus. Now I'm applying the condition. If my, okay, this is the pseudocode I'm just writing. You and I'll be telling you that how to run this pseudocode and how to get the pivot element at the proper position. Okay. So if it says that if my A of L is less than equals to A of P. Okay, we know that. I have told you that if my A of L is less than, it means my left value is less than the pivot value, then it has to go to the left hand side. And if it is on the higher side, if it is greater than the pivot value, then it will go to the right hand side. So how I am going to write it? I am just making it like, because I have made it temporary. So first value will be temporary index equals to my A of L. Okay, first value will come here and index will be plus plus increment. This we have already seen. Okay, again the same thing I am going to do for I equals to L. I is less than equals to H. This is I am going to take because we have to create the two separate arrays in the same array. Okay. Now again the condition I'm applying, if my A of L is greater than, because equal to I have already included here, so I'm not going to use it over here. I'm just including A of P. Okay. So what I'm going to do, I am just writing in my temporary, wherever my index is, just I have to put this A of L and index plus plus. Okay. Now remaining part I'm writing over here for I equals to L, because I have to use this one, but you can say that this is not in place. Sorting is not in place, but the partition sorting could be an in place sorting technique. But you can see from here that for the knife partition, we have to have some other array also. Array is required, right? So now what I am going to do, I am just putting my entire into this one because your sorting is going to be performed on this original array, right? So this is my partition. Okay. Now let's take an example and try to solve it using this concept. Okay. From here we can see that yes, this is going from 0 to n. So it means your time complexity for this particular partition is order of n, and your space complexity is also going to be order of n, as we know, because we have seen that we have to create entirely new array to put our values according to the condition given to us, that with the values less than the pivot value should come on the left hand side and the values greater than the pivot value should come on the right hand side. Okay, so now let's proceed with the exam. Okay, let's first discuss that how we are going to do this. Temporary L minus H plus 1. So let me create an array. If you see, L minus H plus 1 means 0 minus 6 plus 1. So how much it will be? It will be 7. So you can write it, you can change it, H minus L plus 1. I'm sorry for this. Okay, so it will be like 6 minus 0 plus 1. So it will be of temporary 7. Okay, so we have our temporary array of 7 index. It means 6 will be the maximum. 0, 1, 2, 3, 4. Okay, we'll keep on changing it. Okay, right, we'll keep on doing it. Then what is the next value? Your index. This is your temporary array. Index is starting with 0. Okay, my L is 0, H is 0, and P is also 6. H is 6 and P is 6. Now let's see. What it is saying that you have to run a loop from 0 to H. So let's run a loop from I equals to 0, I is less than equals to 6, I plus plus. The complete loop, the entire loop I have to, first of all, I'm going to create the left part and then I'll be creating the right part. So my 8 is the pivot element. This is fixed. This is fixed. So if my A of L is less than A of P, now let's check. A of L is what? A of 0. 5 is less than 8. Yes, condition is true. If it is true, then I'm going to put it inside here. Okay. And then what I'm less than equals to, I'm going to increase my index value from 0 to 1. Now my index will go here. Again, the loop will run 1. 1 is less than, so you can see 13 is less than 8, false. Condition is false. But this loop will run till 6. Remember this. So 13 is less than 8, condition is false. I'm not going to put it over here. Index will remain at 1. Then second, because I will go to 2, right? So 6. 6 is less than 8. Condition is true. So I'm going to put it over here and my index value will become 2. Okay. Then I will go to here. Now see 9. 9 is less than 8. False. Condition is false. It means if it is false, I will remain over. I will be changed to 4 and your index will remain at 2. Now 12. 12 is less than 8. Condition is again false. No change I am going to make. So your index will be remaining at same position, but your I will go to 5. 11 is less than 8. Condition is false. So I'm not going to change it, but your I will go to this position. Now you see here, I will go to here. Then because there is an equality operator is also present. So what will happen? Your 8 is less than equals to 8. Yes, condition is true. Your 8 is less than equals to 8. It means the condition is true. So I'm going to put it over here and my index will become 3. Okay. Now the value has become 7. The I has become 7. So I can get out of this loop because this is completed. Now my next loop says that I equals to 0, I is less than equals to 6, I plus plus. Again, if A of L is greater than A of P, because equality I have already considered. So there is no point I will be considering anything else. Right? Now see, if I have to check both this one, you can go for it. I think I have taken one thing over here. Oh, remember. One second. Just put it over here. 9. Okay. Sorry. Now see, for same conditions, I am writing over here. My index is at third position. Okay. But I will start from here. So 5. Your 5 is less than 5 is greater than 8. False. 13 is greater than 8. Condition is true. I will come from here to here. Okay. Now you can put 13 over here. Right. Our index will become 4. Again, I'll go to 6 because I will go to this particular position. I will come here. Now 6 is greater than 8. Condition is false. Nothing will change into the index value. I will go to third position. You will get 9 is greater than 8. Yes, condition is true. So you're going to put 9 over here and your index value will become 5. Then I will go to here. 12 is greater than 8. Condition is true. And I'm going to put it over here. Your index will become 6. I will go to this fifth position. 11 is greater than 8. Condition is again true. I'm going to put it over here. Your index will become 7 and your I will go here. 8 is greater than 8. Condition is false. When it becomes false, it means that you already been completed with this index. Now you see, then this loop is also gets executed, and the last loop says that the last one, it says that you are just copying the temporary, because you have made this is this is your temporary array. So just directly you are putting all these values inside this one. Now see that we have completed. If you see the resultant array, if you compare this one, 5, 6, 8, you're 13, 9, 12, and 11. Okay, this is my resultant array. If you see, this is a resultant array. Now you can see that 8 was my pivot element. Okay, and all the values less than pivot is on the left hand side, and all the values greater than pivot is on the right hand side. It means in the naive algorithm, we will always get pivot. We will always consider pivot as my last element, and pivot will be placed at such position where from the left hand side you can get that all these values are the minimum values or less than the pivot, and the right side positions will be always the greater ones. Okay, so when you create the quicksort algorithm, so quicksort algorithm, I'm not going to make that quicksort, but just I'm going to tell you, I'm going to write it for you, that your values will be starting mid -1. You're not going to consider this pivot element because this is already placed at its fixed position. You cannot change this pivot value. You know that, right? You can see from here also. This is not going to change. 8 will come over here only. Only the part will change. This 5 or 6. Maybe possible there is 4. So 4 and 5 gets shuffled out. Here you can see this will become 9, 11, 12, 13. But 8 will remain at its position because it is already fixed. So in the naive solution, naive partition, remember this, that you are not going to consider pivot as the part of your quicksort recursive function. Okay, recursive calling. And then the next one will become a mid +1, or you can say pivot. Sorry, I'll take it as pivot. Pivot -1 and pivot +1, comma, your higher. This is going to be your quicksort algorithm when you are considering the naive solution. Okay, so let me give you an example for this also. Okay, if you're going to give this a naive solution. Okay, so this is a kind of a pseudocode which you can create when you're using the naive solution, naive partition. So this way I have explained it to you, the naive method. We will be considering this part, and in the further when I'm going to implement the quicksort algorithm, then I will be showing you the quicksort implementation using this partition. Okay, so thank you.